A Harvard astrophysicist believes there's a strong likelihood this is a craft of alien origin.
Imagine this. For a split second in 2025, the world's biggest telescopes didn't just observe, they blinked in disbelief. 3I Atlas, the hyperspeed interstellar comet hurtling through our solar system at a mind-boggling 130,000 miles per hour, was supposed to keep racing along a clean, hyperbolic exit. This wasn't some local icy visitor, this was an alien from another star system on a one-way trip through our cosmic neighborhood. Instead, its projected dot on NASA's Deep Space Monitor simply froze. No forward motion, no brightening, nothing. It was as if the universe itself had hit pause. Phones rang off the hook, Slack channels exploded with a flurry of confused messages, and a single stunned question ricocheted through mission control. Did that comet just stop? The implications were immediate and terrifying. A body traveling at such speeds doesn't just halt. This wasn't just an anomaly. It was a cosmic impossibility, a direct challenge to everything we thought we knew about physics. The quiet hum of the control room was replaced by a frantic energy, a collective gasp of what on Earth, or rather, what off Earth, is going on?
This video is sponsored by Upstream. Want to grow your YouTube channel faster? With Upstream, you can run a 24/7 live stream using your pre-recorded videos. Since live streams rank higher in search, you'll gain more views, more subscribers, and more revenue. And it's not just YouTube. Upstream lets you multi-stream to up to 10 platforms, design custom layouts that match your brand, and schedule your content so your channel is live even when you're not. Sign up free today with the link in the description, and if you decide to upgrade, you'll get 20% off your first month. Start streaming smarter with Upstream.
Scientists have been tracking 3I Atlas, officially known as C2019 Q4 Borisov before its interstellar designation, since its discovery. And from the get-go, it was a weird one. It came in hot, already spitting carbon dioxide jets way out near Jupiter's orbit. That's a staggering 6 times farther from the Sun than Earth, a place where most comets are practically napping, completely inert. Comets normally stay quiet until they get much closer to the Sun, where the heat can start to vaporize their ices. Not 3I Atlas. It was active, unusually so right from the start. Then, in the hours leading up to its closest approach, every single observatory, every update, showed the same celestial coordinates. The ephemeris, the detailed table predicting its position, flatlined. For a moment, the collective astronomical community held its breath. Twitter, of course, went wild. Alien handbrake? Is ET pulling a fast one? But inside the Jet Propulsion Lab, a quieter, much chillier fear took hold. If gravity alone had somehow been switched off for this one object, if a body traveling at 130,000 miles per hour could just decide to stop, then physics itself was fundamentally broken. This wasn't a glitch, it was a paradigm shift that no one was ready for. The implications were dizzying, almost philosophical. What if the laws of the universe weren't as universal as we thought? The panic wasn't just theoretical, it was operational. Duty astronomers slewed every free eye they had. Hubble, the mighty James Webb Space Telescope, even the Mars Reconnaissance Orbiter, toward the last known pixel where 3I Atlas was supposed to be. But there was nothing. It was like staring into the void where a ghost had just stepped out of its own trajectory. The emptiness was deafening. No glowing coma, no faint smudge of a nucleus, just black. Programmers, fueled by an almost supernatural blend of adrenaline and caffeine, hacked together orbital patches in minutes. Postdocs who hadn't slept since the weekend had begun mainlined coffee and rewrote scripts to widen the error ellipse, hoping to catch even the faintest whisper of the comet's presence. Still, silence. Had the comet become transparent, somehow cloaking itself from our view? Had it disintegrated into an invisible dust cloud? Or, the most unsettling thought, had it been swallowed by some micro-black hole no one had noticed, a cosmic predator lurking unseen in the dark? Panic, a raw primal fear, crept from the control rooms into the media. Headlines screamed that the interstellar visitor had vanished, or, more ominously, had chosen to halt. The public, already fascinated by this cosmic interloper, was now gripped by a blend of fear and wonder. Was this an omen, A sign. The scientific community, meanwhile, was grappling with a crisis of observation and interpretation. How could something so massive, moving so fast, simply disappear? The race to reacquire wasn't just about finding a comet, it was about reaffirming our understanding of the cosmos. 17 tension field hours later, just as despair was beginning to set in, a faint whisper emerged from the Canada-France-Hawaii telescope. It caught a smudge, a barely perceptible anomaly 8 arcseconds west of the predicted path. It was faint, elongated, and peppered with what looked like mini-nuclei, like beads on a cosmic string. It wasn't the single, bright point they expected. It was fragmented. 3I Atlas had not stopped, it had fallen apart. The coma that once faced the sun, a distinctive teardrop-shaped dust cloud, now stretched sideways, a glittering, diffused teardrop of shards coasting on slightly different tracks. Each individual fragment was too small to push back enough light for early detection, so for a nerve-wracking day, the combined brightness of the comet dipped below the threshold of our most powerful telescopes. In plain English, the comet didn't hit the brakes, its headlights just went out. And with those headlights, our ability to track it, for a crucial period, vanished. The relief in mission control was palpable, followed by a new wave of scientific intrigue. Why had it broken up, and what could this tell us about interstellar objects? Comets, despite their majestic appearance, are incredibly fragile. Think of them not as solid rocks, but as dirty snowballs spun by a child, a delicate mix of carbon dioxide ice, water ice, dust, and other volatiles, all held together by self-gravity and the gentle forces of its own spin. Take it far from starlight, and it stays pristine, a frozen time capsule. But bring it inward, or, in the case of 3I Atlas, whip it around at a staggering 58 kilometers every single second, and things get interesting.
Thermal stress from the sun, tidal tugs from nearby planets, or even uneven jets of gas from sublimating ice can torque the nucleus until it shears. 3I Atlas was a prime candidate for this kind of cosmic unraveling. It started venting CO2 way out at 6 AU near Jupiter's orbit, far earlier than expected for a typical comet. This super early activity wasn't just unusual, it was a red flag. It puffed the coma to an incredible 8 times the CO2 richness of any native comet we'd ever observed. This meant immense internal pressure was building up within its icy structure. Cracks, invisible from afar, widened steadily, and the centrifugal force from its own rotation, combined with the stresses of its high-speed journey and early outgassing, simply finished the job. The comet didn't even need the sun's full, intense heat to break apart. It merely needed time to shake itself to pieces from the inside out. It was a ticking cosmic time bomb, and we were watching the explosion in slow motion. Before the breakup, initial models, based on its brightness, predicted a nucleus up to a formidable 5.6 kilometers wide. That's a significant chunk of space rock. But post-breakup photometry, analyzing the light from the scattered fragments, dramatically shrank that upper limit by an entire order of magnitude. What we thought was a single solid body was in reality a much smaller, far more volatile entity. Where a single, seemingly robust body had been, at least 30 distinct fragments now coasted, each shedding an astounding 40 kilograms of water every second. That's 40 kilograms of precious water that before the split fed one single deceptive light curve. Hubble's new, sharper images revealed the collective surface area of these fragments had jumped almost 5-fold. This meant that total outgassing surged, even though the individual pieces were cooler. Why is this such a big deal? For planetary defense experts, this is the nightmare scenario made real. A celestial body can masquerade as benign, a single predictable target, then suddenly multiply its surface area without warning, turning one potential impactor into dozens of smaller but still potentially hazardous projectiles. It's not about Hollywood heroics or Bruce Willis saving the day. It's about cold, hard math that keeps specialists awake at night. Managing a swarm of smaller, unpredictable objects is exponentially more complex than dealing with one large one. This wasn't just a scientific curiosity,
It was a stark lesson in cosmic risk assessment. Interstellar visitors are inherently mysterious. They arrive unannounced from unknown birthplaces, carrying secrets from beyond our solar system. 3I Atlas, we now understand, hails from the thin disk edge of the Milky Way, a zone poorer in metals and significantly older than our own sun. This ancient origin is crucial. If comets that form in these older, metal-poor regions are inherently more fragile and fragment more easily, then every future rogue comet we encounter could detonate earlier than expected. This single profound insight forced NASA's Small Body Assessment Group to reopen dusty papers on torques, tensile strengths, and volatile ratios. We may need to fundamentally change how we perceive these interstellar interlopers. They might not be sturdy cannonballs as we once imagined, but rather delicate, fractal snow roses ready to burst under the slightest stress. This isn't just an academic debate, it has real-world consequences. The cost? Recalculating how we'd even attempt to deflect or rendezvous with one of these objects on short notice. If they're prone to fragmentation, our current strategies for planetary defense might need a complete overhaul. It's a humbling reminder that the universe still holds countless secrets, and each new visitor brings with it the potential to completely rewrite our textbooks. If break-apart space rocks and cosmic mysteries make your head spin, and you want to stay ahead of the next cosmic surprise, then you've found your tribe. Hit subscribe, ring that bell, and tell the algorithm you're one of us space nerds who likes their physics served with a side of goosebumps. Join our journey as we unravel the universe's most mind-bending phenomena, one astonishing discovery at a time. So, what's the future for the scattered remnants of 3I Atlas? Its fragments will continue their journey, whipping around the Sun on October 30th, 2025 at about 1.4 AU, just outside Earth's orbit, before slinging back into the vast, dark emptiness of interstellar space. By December, the fragments will dim beneath even JWST's incredible threshold, gone for good, perhaps to wander the galaxy for eons more. But the hunt doesn't stop there. Telescopes will continue to scrape the sky for the next I object, 4I, 5I. Each new letter carries the exciting possibility that the chemistry, spin, or breakup profile will again rewrite the rules, challenging our models and expanding our understanding. Meanwhile, NASA engineers are running supercomputer models, loading each shard's measured velocity to see if any chunk, however small, might graze planetary space decades or even centuries from now. It's a painstaking, long-term calculation. Spoiler alert, current risk is zero, which is a huge relief. But the data set gathered from 3I Atlas is pure gold for future intercept missions, providing invaluable insights into the behavior of these unique cosmic travelers. It's about building a library of knowledge, one interstellar encounter at a time, preparing us for whatever the cosmos might throw our way next. You might be thinking, okay, a crumbling snowball, interesting, but why should I care? Well, Earth's history, and indeed the history of life on our planet, is profoundly sculpted by impacts. Remember the dinosaur killer? That was a roughly 10-kilometer rock, not much bigger than the original pre-breakup estimate for 3I Atlas. Understanding how easily comets fragment tells us crucial things about the potential for future impacts, specifically how often cities or even entire continents might face cluster bombardments from fragmented objects. It's a matter of planetary safety, a lesson in cosmic defense. But there's a more romantic, even profound reason to care. Those interstellar shards carry intact interstellar chemistry. When they vent carbon dioxide and hydrogen cyanide into our solar system, they're not just making a mess, they're seeding the outer solar system with organic feedstock. These are the very ingredients that billions of years ago might have helped life spark here on Earth. Every breakup, every puff of gas, every scattered fragment is a powerful reminder that we ride a thin raft through a shooting gallery packed with both peril and promise. These visitors are not just threats, they are messengers, carrying the building blocks of life and the secrets of star systems far beyond our own. So 3I Atlas never truly stopped. It simply fell apart faster than our software could retune. Yet for those frantic hours, the illusion of a motionless comet forced the world's smartest astrophysicists to question Newton himself, to grapple with a cosmic anomaly that defied all logic. The real jolt wasn't paranormal, wasn't aliens hitting a brake pedal. It was the humbling reminder that a fragile snowflake, older than the sun itself, can glide across the vast expanse of the galaxy, shatter under the gentle stresses of a new star, and humble an entire planet's worth of experts in a single day. It's a testament to the universe's endless capacity for surprise, a cosmic curveball that reset our expectations. Keep watching the skies, because the next interstellar visitor might not just break apart, it might just break our assumptions wide open and redefine what we think is possible.